Hello everybody, welcome back to the second class about pumps. This is the pump scaling lesson. Today we're going to build on what we talked about last time, but of course before we start, we have something to take care of. We need to look at our next open-ended problem. So let's go ahead and take a look at what that will be like. Oops.
Following my footsteps. Nothing can touch the surface other than where I stand.
Okay, so Prince of Persia, unable to stop a pebble from hitting the sand trap, Dastan falls along with the coursing sand toward the chasm by way of a slanted stone wall. At the end, right before plummeting into the bottomless crevice with the sand, he is able to stop himself and grab onto a stone column. In reality, how fast would Dastan have been moving, and could he have stopped on that narrow column? Hint. Think 1D Navier-Stokes here. I'm sure many of you are saying that's a crappy hint. Oh well, that's the hint you get. So, a little bit of a check just to see what's going to happen. You're going to check to see what would happen if the falling blocks of stone were there. In other words, for the first part, you can assume they're not for simplification. How would that impact the process? Part B is 1D flow, reasonable approximation in this case. Part C, aside from the asymmetry effects of part A, is this method, simplifying of the Navier-Stokes, reasonable? What about the sand makes the solution questionable? For this, think back to the very first day of class when we talked about scales and whether it's a continuum or not a continuum. And then based on your answer to part one, generate an expression for the volumetric flow rate as a function of the sand properties and the sand flow thickness. So this should be similar to what you've done before, but I wanted to give you more practice doing Navier-Stokes. Okay? A little bit of a roadmap. Again, we're towards the end of the fluid system analysis. We're looking at pumps we did last time and today, and then next time on Friday when I'm back, we'll be doing turbines or turbines, depending on how proper you feel like being. Okay? So today, we talked last time about pumps in general and how they can work in a system. Today we're going to talk about how to combine pumps to create a system. This will have a very similar flavor to what we did for pipe networks. We're going to look at combining pumps in series and in parallel and how we can determine what order and placement we need in order to make the pumps do what we want them to do. Then we're going to look at scaling of pumps. Okay, because a lot of times you'll have a pump already that's operating, but you'll want to look at it operating in a different mode or location. You'll want to use a different fluid. And so what you'll need to do is you'll need to apply scaling laws to see how you can translate that pump to another application. Again, pumps only work in one mode, on. And so how you put them in and how you arrange them makes a big difference in how the system is operated. And then finally, we'll talk about how to select the right kind of pump. And then we'll go through example 1460 in the book. Okay? So for pump combination in series, really the goal is to increase head for the same flow rate. Because these pumps are in series, you have to have the same flow rate in order to satisfy the continuity equation, or as you all know by now, the mass balance equation is the continuity equation. So in order to make sure that we're not accumulating mass, the flow rate has to be the same. So what the second pump does really is to add a greater head. So basically, these are additive. The total head will be equal to the head of the first pump plus the head of the second pump. So if we draw a system curve, just like with pipe networks, where we have the head on the left side and the volumetric flow rate along the bottom, this means we add the two pump performance curves vertically. Okay, so this is similar to pipes in series. Pumps in series and pipes in series can be added the same way. You add that head performance curve vertically. So in other words, the brake horsepower total is going to be the brake horsepower of pump 1. As we can see over here, we have pump 1 plus 2. That means the new performance curve follows along this line here, the total curve. So it's curve 1 plus 2 as long as there is a 1 plus 2. And once that's done, then that system curve for the pumps drops just down to pump 2. What does this mean? Well, this is one of the challenges of operating in series. The benefit is that you can indeed have a higher head with the same flow rate. So if your system curve looks something like this, then you would be able to operate much higher if you have the two pumps together. However, past this point where one hits the free flow point, that's the challenge, because if you're trying to operate out in this range, then it's possible that you could be operating pump 1 beyond the free delivery point. In other words, past the point where you have 0 head maximum flow rate. So then that means pump 1 becomes a loss. Instead of providing head to the system, it's actually serving as a sink for head. It's serving as a flow loss because you're trying to push flow faster than can be allowed through pump 1. This is the fastest flow rate pump 1 can allow. If you pump out here, suddenly you're pushing against the pump blades, and you are creating a loss rather than providing head. So that's one of the risks of adding pumps together vertically, or in other words, in series, is if they are not the same size, then you could run beyond the free delivery point of the smaller pump. Not only does that become a loss, you can damage the pump by stripping different components or ruining the magnetic coupling. Okay? And so therefore, this is a great option for increasing your head, but you want to be very careful that if you're using pumps of different size, that you're not operating above the free delivery point of the smaller pump. Okay? So oftentimes what they'll do is they'll actually end up with a shutoff valve, a shutoff valve and a bypass valve, so that the smaller pump can be bypassed if the flow rate increases beyond the free delivery of that pump. So you would close this red valve here, and that would prevent pump or flow from going through that second pump or the smaller pump, and then you would send bypass through this green valve. You'd open up this bypass valve. And basically what that does is you would, at this point, where you're beyond pump 1's free delivery point, you simply open up or close up pump 1 and only run through pump 2, because at that point pump 2 and the system pump curve are exactly the same. Okay? The other option is for combining pumps in parallel. Just like in parallel pipe networks, you are going to have the same pressure drop or the same head for the pumps in parallel. And what you're really going for here is to increase the volumetric flow rate. Okay? So just like with parallel pipe networks, the total head is equal to the head of each pump, and the total volumetric flow rate is equal to the sum of the volumetric flow rate through each parallel path. Now, where might you see something like this? A good example is in a nuclear reactor. You need a very large amount of flow, about 100,000 gallons per minute for the Westinghouse SMR, which is the small version of nuclear reactors. There are not many pumps that can provide 100,000 gallons per minute at high pressure and high head loss. So what we actually have to do is we actually have to put 8 of those pumps in parallel. and it almost looks like helicopter blades. They stick them out of the side of the top of that nuclear reactor. And basically, they each will provide 1/8 of the needed volumetric flow rate. So adding up all those 8 pumps will get you the total flow rate that you need. And so again, looking at the system curve, if we were to have pump 1 and pump 2 like this, just like for the parallel pipe networks, we're going to add these curves horizontally. So you see that pump 1 here is added to pump 2 horizontally here to provide the total system curve. Okay? So if we're interested, if we have a system curve, or in other words, the pressure drop per flow rate, like what you did for the pipes, then what we do is look at where those two intersect, like we talked about last time, and that gives us the operating point. And then we can see exactly what the flow rate is through each of the pumps by following the head loss across. Since again, it's going to be the same pressure loss across both. So we can see that pump 1 has a volumetric flow rate of this magnitude, pump 2 has a volumetric flow rate of this magnitude, for a total flow rate here, which indicates the actual operating pump of the parallel pipe network. So again, just like parallel pipes, the head curves or the performance curves of parallel arranged pumps is that you sum them in the horizontal direction. So in other words, the brake horsepower total is the same as the brake horsepower of each individual pump added together at the operating point. Okay? So in other words, the total work horsepower is equal to rho GVH total, where the efficiency is equal to rho GVH total over the brake horsepower total. Okay? Here's the problem with running pumps in parallel, or the risk. If the system head is greater than the shutoff head of the smaller pump, then you'll actually potentially get reverse flow through the smaller pump. So in other words, if we get to this point where we're beyond the system curve and run up into this region here, where only pump 2 is at that sufficient head, then that's a greater head loss than you see through the maximum head of pump 1. So you will actually get flow that will come through pump 2 here, and then it will actually backflow because it's a lower pressure than this point. And so you'll get reverse flow through a pump, which can cause significant damage. So, just like with the pumps in series, what they do is they create a shutoff valve. This time we don't need a bypass valve because we're not trying to continue the flow to the network. We have a flow path through pump 1. What we do simply is shut off this valve so that there is no flow backwards, there is no pressure differential in that path, and then flow continues as normal through this path. Okay? So a lot of times, when you're in industry, you'll have a pump already, and you'll either want to change how that pump operates, or you'll want to consider pumping a different fluid through there. If you change one of your chemical reactors and you have a different product, you'll want to see what kind of changes you need to make to your pumping system or to your pump in general. And so you might want to change fluids, or you might want to design your system to operate at different conditions. Any of these are viable things that you might experience as a system engineer or as a chemical engineer. And so we want to talk about how to do that. In this case, we're going to use what we call the pump scaling laws. And these scaling laws were developed using the same dimensional analysis that we use to look at turbulent flow and laminar flow and a couple other things. So we're going to look at the pump parameters. This is going to look familiar to you since we actually did this on the test. You're going to look at the impeller diameter, the flow rate, the rotational velocity, the density, the viscosity, and the roughness. Okay? So in this case, how many parameters do we have? We have 6. How many dimensions do we have? We have 3. That means we are left with 3 pi groups. Okay? We have a pi group for the flow, we have a pi group for the Reynolds number, and we have a pi group for the roughness. You'll notice these two are analogous to pipe flow. What we've really added is the coefficient of volumetric flow rate here, CQ. And that is our third pi group that we have beyond typical simple pipe flow. So what are the properties of interest that we want to be scaling or looking at? Well, the things we really want to look at are the head, the brake horsepower or the power, the efficiency, and the net positive suction head. Those are the 4 parameters that we want to make sure that we match appropriately. So what we're going to do is we're going to non-dimensionalize these parameters because these are the ones that are of interest to us using the pump parameters. Okay? So what we do is we take the head and we apply by the different parameters to non-dimensionalize the head. And what we end up with is the coefficient of head, and that is a function of the coefficient of flow, the Reynolds number, and epsilon over d. Again, you'll notice that for all 3 of these, they are a function of our pi groups, which are the same as regular pipe flow pi groups, plus now we have the coefficient of flow. Okay, so we define a head dimensionless number, a power dimensionless number, and an efficiency dimensionless number. Okay? And what we can notice is that for high Reynolds number, the impact on these parameters of the Reynolds number decreases, just like the friction factor F decreased in pipe flow as Reynolds number increased. If you remember on the Moody diagram, those lines leveled off and became smooth without any appreciable decrease after time. It's what we call fully turbulent. That same thing happens in a pump. The impact of Reynolds number decreases as the Reynolds number gets larger. And so we can, for all intents and purposes, in high Reynolds number flows, neglect that. Not only that, what we find is that in pumps, the roughness differences are very, very, very small. In pipes where you have long distances that you're flowing, they make quite a large difference. But in a pump, it's a very small area. It's a very small length. And relative to the losses you get from spinning blades, the roughness losses are extremely slow. So what we learn based on that is that effectively the performance of the pump is solely a function of the coefficient of flow rate. Okay? Now this is described in the book, in the affinity laws. It looks like I didn't put a page number. I hadn't quite found it in both versions yet, but the affinity laws are located in the reading chapter for the day. And those affinity laws describe how the coefficient of flow rate can be applied in order to do pump scaling. Okay? So in order to scale the pumps, what we need to do is we need to match the groups, just like for experimental analysis. Remember with the open-ended problem with Doc Brown, in order to compare the model train to the full-size train, we wanted to match the Reynolds number or the dimensionless group. And here what we're going to do for pumps is we want to match these groups just like we did in those problems. Okay, so let's go through an example. For a given coefficient of flow pump with a speed omega rotations per minute, if that omega doubles, what is the new volumetric flow rate, the new head, and the new power? Okay, so in other words, we're given a pump with a coefficient of flow rate, CQ. The speed doubles. What does that do to the new volumetric flow rate, head, and power? Okay, so where do we go? How do we approach this? Well, let's go back to these dimensionless numbers. You see up here we have the dimensionless number for head, power, and efficiency. The first question is how does it impact the flow rate? Okay, so what does it look like? That's efficiency. The first question is what does it do for flow rate? Okay, so what we can do is we look just at the CQ number. How is flow rate impacted there? How is it correlated with the speed? Well, we notice that if the speed goes up by a factor of 2, in order to keep the same coefficient of flow, the volumetric flow rate also has to go up by 2. And sure enough, that's how we correlate it. If the RPM doubles, then the flow rate also doubles. Okay, so that's what we do for flow rate, is we look at this coefficient of flow rate. Now it wants to know about head. Okay, so let's come back up here and let's look at the head number. How our head, or CH, how is the flow rate, how does the rotational speed compare with the head? The rotational speed is squared. So if you double the rotational speed, what does the head have to be in order to maintain the same dimensionless number? Well, 2 squared is 4. That means you have to increase the head by a factor of 4. So let's come down here. And sure enough, if we double the rotational speed, the head has to increase by a factor of 4. Let's finally look at power. So we come back up here to the power number, coefficient of power. And again, we're told that the omega increases by a factor of 2. So 2 cubed is going to be 8. So in order for the brake horsepower to be how we have to change the brake horsepower in order to maintain the same CP is that we need to increase it by a factor of 2 to the third or 8. So sure enough, as we look at this, as we compare the two brake horsepowers in order to maintain the same coefficient of pressure, of power, that means if the speed doubles, we need to increase the brake horsepower by a factor of 8 in order to maintain the same coefficient of pressure. So that's all we're doing really for the scaling laws, is we're using those dimensionless numbers to evaluate how the pump's performance would change given some difference in pump operation. In this case, we decided to double the speed. We adjust the motor such that we can double the speed. In that case, we'll have double the flow rate, we'll have 4 times the head, and we'll have 8 times the power requirement. Okay? So the last thing we want to look at is how to select a pump, how to pick the right size and right type of pump. So there's a number, another dimensionless number called the pump specific speed. Now in the book, you'll notice that not only does it have the specific speed NSP, it also has NSP British, NSP US. Here's the challenge. You see the graph down at the bottom, that's in NSP US, right down here. Here's the problem. A lot of engineers are too lazy to figure out how to non-dimensionalize a number, so they'll just use English or British units and turn a dimensionless number, like NSP, into a dimensioned number. That means things really ugly and really, really messy. So my number one piece of advice to you is keep the NSP dimensionless. There's no need to make it complicated by adding your own funky units. Whenever you calculate NSP, it will be much, much easier to keep it dimensionless. However, not everybody does that, and even pump vendors do not keep it dimensionless. So at times you are going to want to be able to translate between one or the other, and the book has different plots to let you do that. But the easiest way to do this is to keep NSP dimensionless. Anyways, I digress. The specific speed is how you determine what kind of pump that you need. How does it work? Well, what we do is we use the coefficient of flow and the coefficient of head, and this specific speed is equal to the coefficient of flow to the 1/2 power divided by the coefficient of head to the 3/4 power. That is the definition of the dimensionless number known as the specific speed. And there's a lot of things we can tell based on empirical correlations using the specific speed. First of all, what's been done is the efficiency has been plotted versus the specific speed for 3 different types of pump. Okay? Again, the note here to being careful of the units. But let's say, for example, you have a pump and you evaluate the specific speed to be 2. So you'd come down here to a well-known plot and you'd find that right here is where your specific speed falls. So the best choice for you would be a mixed flow pump. And the efficiency of that would run at around 89%, as you can see right here. So what do these mean? Well, I drew in the arrows so you can kind of see. Last time we talked about the different kinds of pumps. The radial or centrifugal pump are the pumps where the flow comes in axially and leaves radially. Those are probably the most common types of pump. And as long as your specific speed is less than around 1.5, you will be able to have and effectively use a centrifugal pump. However, as a consideration beyond that point, you'll notice that if your specific speed is around 1 or so, you'll end up with a maximum efficiency. So this is something to consider when you're selecting pumps. Not only what type of pump, but can you size it so that the specific speed is right at that maximum efficiency point. If you have a specific speed between 1.5 and 3.5, you'll have what's called a mixed flow pump. It's not quite axial, where the flow goes straight through. It's not quite centrifugal, where it goes in and then is radially dispersed, but it is somewhere in between, at around a 45-degree angle. Anywhere between 20 to 80 degrees or so could be considered a mixed flow pump. Okay? Now, if you have a very fast pump or a very high specific speed, so that's, again, the coefficient of flow to the 1/2 divided by the coefficient of head to the 3/4, then you're going to be looking at an axial pump, and that will be the best type of pump operation. And you can look here to see that where the maximum efficiency would fall somewhere around 4.5. So that's how you pick what type of pump you want to use, is you evaluate the specific speed and then see where that falls on a plot like this. There's a very detailed plot given in your book where you can look and see what kind of pump you should select. Okay? So that's the gist of pump scaling. Simple in concept, and pump networks, where you're going to be looking at how many pumps you want in series or in parallel. And I highly recommend that you really look over and understand how to add pumps in series and parallel. It's the same as for pipes, but you're going to be dealing with the supply instead of the system losses. So again, as a review from last time, this curve that you see along the bottom represents the system curve. It represents the head loss or the pressure loss of a system based on the flow rate. This is exactly what you were drawing in the graphical method for the pipes. So this system curve shows you the total head loss for an entire system. Okay? And then these pump curves illustrate where the pump will operate. And in order to do parallel flow, you're going to have horizontal additions, so this becomes the total flow rate. You do curve 2 until you get to the point where curve 1 contributes, and then you have the sum of those, and this provides the total pump flow rate. Okay? And then the same thing for series, except this time you're adding vertically. So make sure that you understand this very well. It's a key point, and you most certainly will see it on the assignment. Make sure you understand pump scaling, how to use these dimensionless numbers here, head, power, and efficiency, or in other words, CHCP and eta, which you've already had experience with, but it's defined again here for clarity. Make sure you understand how these work and how you keep them the same to maintain pump operation and pump performance when you're scaling to different systems. Okay. Finally, we can go through the book problem. This is an MPSH problem. It's example for, actually it's full-on book problem 1460. Okay, so the point of this problem is if you're given a diagram and key parameters of a system, you should find the max volumetric flow rate that avoids cavitation in the pump or in the system. When you think of cavitation, what comes to your mind? That's right, you should be considering net positive suction head. Okay, so we start off by giving you this diagram and illustrating that your points are here and here. We define the diameter as 1.2 inches, the length is 12 feet. We have the minor loss for the entrance, for the bend, and for the valve. The density of water is defined, the viscosity of water is defined, the total height difference is 20 feet, and then we have a curve for the net positive suction head. It's 1 plus 0.0054 times the flow rate squared. Again, Q is not heat transfer. This is the very ineffective swapping between V dot and Q. Q is the flow rate, and the units on Q are gallons per minute. Okay, and this net positive suction head is an empirical correlation, and so what it tells you is that you get that answer in feet, but you have to use Q units of gallons per minute. Okay, and then the saturation point for water is given as 0.46407 pounds per inch squared. So how do we do this? How do we approach this? Well, what we do is we start with the energy equation. Okay, and what we do is we balance based on our points. We cross off the velocity 1 because we're taking point 1 at the top of the tank here, and so it's 0. Z2 is at the bottom of the system, so the height is 0 there. Okay, the G shouldn't be crossed off. That'll maintain there. The reason it's crossed off here is we actually have written it down below, but don't think that we're getting rid of it. We're just dividing everything by G. So now there's a G term over here and G term here. Anyways, like the energy equation, we have those 3 types of energy, and they're balanced by the pipe loss and the minor losses. Once we've done that, we want to write down and recognize the equation for the net positive suction head, which was defined in the last lecture, and it can be seen right here. Once we've done that, once we rearrange the energy equation, once we've crossed off V1 and Z2, we rearrange this so that we have the new and updated energy equation. And then we recognize that one of the terms in the net positive suction head is P2 over rho G. So we can solve this equation for P2 over rho g and then insert that equation right here. And that's what we've done. We've inserted that equation and then solved for net positive suction head. And so we have this expression, which is the energy equation, where we have applied the manipulation of subtracting Psat and rho g plus P1 over rho g for the net positive suction head. And you remember, we defined an expression for the net positive suction head right here. So we set the energy equation that we've now set equivalent to net positive suction head by inserting this equation into the energy equation. We set that equal to the expression for the net positive suction head that we had on the previous page. Okay? Recognizing that we need to use the appropriate units. Then we use as a subsequent equation. Right here, we have 3 unknowns. So we use a subsequent equation where we define Q as equal to pi over 4 d squared times velocity. Or in other words, the velocity times the area is the volumetric flow rate. For our third equation, because we don't have F either, we use the Colebrook equation to develop an expression for F. Once we do this, you can simply do a system of 3 equations and 3 unknowns. In this case, you can solve with MathCAD to find out that the flow rate for this system to prevent cavitation is 56.6 gallons per minute. So again, we're doing the same thing that we've done before. We're using the energy equation to set up the system. All we're adding this time is the requirement that this is the condition that must be satisfied in order to maintain sufficient suction head that we do not cause cavitation in our pump. So we're manipulating the energy equation to account for the net positive suction head. We're defining the flow rate, and then we define the friction loss. And by doing that, we can say that the minimum flow rate to prevent cavitation is 56.6 gallons per minute. So this was fairly short, brief, and succinct. Hopefully you understand. If not, please send me an email and let me know so that I can help you work your way through it. It should be fairly straightforward. Again, please let me know if you have any questions. And other than that, I will see you guys Friday. Thank you very much.